that experiences a force when placed in an electromagnetic field. Electric charge generally can be either positive or negative. The presence of electrical charge in a body can be determined by the number of electrons present in a body. Once a body loses electrons, it is said to be positively charged. When a body gains electrons, it is said to be negatively charged. The charge is said to be quantized. How can you say that the charge is quantized? It can be demonstrated by using the formula Q is equal to plus or minus N into E. Here total charge on any body is always an integral multiple of basic unit of charge E. Here the plus sign indicates that the charge is to be positive, minus sign indicates that charge is said to be negative. Therefore, around any charge, there is an extent up to which its influence is manifested. The extent up to which its influence is present around a charge is called electric field. The electric field strength or electric field intensity can be defined as the force experienced by unit positive charge placed at that point. Therefore, electric field intensity or electric field strength E is equal to F by Q. It can be formulated as E is equal to F by Q. Therefore, the force experienced by unit positive charge placed at a point in an electric field is electric field intensity. E is equal to F by Q, which can also be written as 1 by 4 pi epsilon 0 into
4 pi epsilon 0 into Q by R square.
By the way, suppose there are two charges Q1 and Q2, which may be either positive or negative or positive or negative, positive negative. The force of attraction or repulsion between these two charges can be determined by using the formula Coulomb's law. It can be understood by using the Coulomb's law. According to Coulomb's law, the force of attraction or repulsion between two charges is directly proportional to the product of the charges and is inversely proportional to the square of the distance between them. Therefore, F is proportional to Q1 into Q2. F is inversely proportional to R square. These two relations can be combined together by using F is proportional to Q1 Q2 by R square. F is equal to some constant K into Q1 Q2 by R square, where K can be taken as 1 by 4 pi epsilon 0, where epsilon 0 is the permittivity of free space or vacuum.
If two equal and opposite charges separated by a certain distance is called an electric dipole. Here consider an electric dipole consisting of two equal and opposite charges minus q and plus q, which are separated by a distance 2a. These two charges are located at A and B. What is the distance between these two charges? 2a. Let P be a point on the axial line of a dipole at a distance smaller units from its center. Then distance of P from B is r minus a, and the distance of A from P is r plus a. Now we have to write the intensity of electric field at P due to plus Q is E1 is equal to 1 by 4 pi epsilon naught into Q by r minus a whole square, and also intensity of electric field at P due to minus Q is E2 is equal to 1 by 4 pi epsilon naught into Q by r plus a whole square. Now resultant intensity of electric field due to the dipole at P is E is equal to E1 minus E2. Therefore, E is equal to 1 by 4 pi epsilon naught into q by r minus a whole square minus q by r plus a whole square. On taking q as common factor, q by 4 pi epsilon naught into r plus a whole square minus r minus a whole square by r square minus a square whole square. On taking LCM in the bracketed term, we get r plus a whole square minus r minus a whole square by r square minus a square whole square. So we know that a plus b whole square minus a minus b whole square is equal to 4ab, which can be applied in the bracketed term here. That is equal to q by 4 pi epsilon naught into 4ar by r square minus a square whole square. That is equal to 1 by 4 pi epsilon naught into, let us bring this q into the bracketed term, thereby we can rewrite it as 2 into q into 2a into r by r square minus a square whole square. Therefore, E is equal to 1 by 4 pi epsilon naught into q into 2a is dipole moment 2p r by r square minus a square whole square. Since r is very greater than a, we can neglect a square term here. Therefore, E is equal to 1 by 4 pi epsilon naught into 2pr by r square whole square, that is equal to r power 4. Therefore, E is equal to 1 by 4 pi epsilon naught into 2p by r cube. Define intensity of electric field at a point. Derive an expression for the intensity due to a point charge. The intensity of electric field at a point in space is defined as the force experienced by a unit positive charge placed at a point in the field. Suppose F is the force experienced by a test charge Q which is placed at a point in an electric field. The intensity of electric field at that point E is equal to force per charge, force by charge. Here let small q be the test charge which is brought near to a point charge q. Let us assume that P is a point at a distance small r from a point charge q. According to Coulomb's law, we can calculate the force between these two charges, capital Q and small q. F is given by 1 by 4 pi epsilon naught into q by r square. On taking this small q to the left side, it will divide. Therefore, F by q is equal to 1 by 4 pi epsilon naught into q by r square. So, from 1 and 2, we can write E is equal to F by q is equal to 1 by 4 pi epsilon naught into q by r square. Therefore, intensity of electric field due to a point charge is given by 1 by 4 pi epsilon naught into q by r square. By the way, now we are going to derive an expression for the intensity of electric field at a point on the equatorial line of an electric dipole. The line that is passing through the center and perpendicular to a line is called equatorial line. Suppose here two charges minus q and plus q which are separated by a distance to a. Minus q and plus q are respectively located at a and b. Let P be a point on the equatorial line of a dipole at a distance r from its center. Now we are going to calculate the magnitude of electric field at P due to plus q, magnetic field of electric field at P due to minus q. E1 is equal to 1 by 4 pi epsilon naught into q by r square plus a square. According to the right angle triangle here, AP or BP is equal to root of r square plus a square. So E1 is equal to 1 by 4 pi epsilon naught into q by r square, 1 by 4 pi epsilon into q by root r square plus a square whole square, that is equal to r square plus a square. The magnitude of electric field at P due to minus q is 1 by 4 pi epsilon naught into q by r square plus a square. From the figure, it can be understood that y components of electric field E1 and E2 are equal and cancel each other. But the sum of x components gives rise the resultant field at P. Therefore, intensity of electric field is E is equal to E1 cos theta plus E2 cos theta. Their cos theta can be written as q by r square plus a square, that is equal to 1 by 4 pi epsilon naught into q by r square plus a square cos theta plus 1 by 4 pi epsilon naught into q by r square plus a square cos theta, that is equal to 2 into 1 by 4 pi epsilon naught q by r square plus a square cos theta. Here cos theta can be written as a by root r square plus a square. Therefore, E is equal to 2qa by 4 pi epsilon naught into r square plus a square whole power 3 by 2, that is equal to E is equal to 1 by 4 pi epsilon naught into r cube. Since r is very greater than a square can be neglected. Therefore, electric field intensity of the electric field at a point on the equatorial line of dipole is 1 by 4 pi epsilon naught into p by r cube. Know that capacitor is an electrical device which is used to store electrical energy. A pair of conducting plates separated by a certain distance is called a capacitor. Consider a parallel plate capacitor consisting of two parallel plates of each area A separated by a small distance d. Let V be the potential difference applied between these two plates. The charges of the plates are plus q and minus q. Now we have to find out the surface charge density on these two plates. Electrical field surface charge density on the plate 1 can be written as sigma is equal to charge per unit area q by a. At the same time, we have to write electric field due to a plate 1 is sigma by 2 epsilon 0. Similarly, electric field due to plate 2 is minus sigma by 2 epsilon 0. Electric field between these two plates E is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, which is equal to sigma by epsilon 0. But from 1, sigma is equal to q by a. Therefore, it can be formulated as E is equal to sigma by a is equal to q by epsilon 0 a. The field inside the capacitor E is equal to q by epsilon 0 a. But we know that E is equal to V by d. V by d is equal to q by epsilon 0 a. But charge q is equal to capacitance into potential difference q is equal to Cv. That implies V by d is equal to Cv by epsilon 0 a. So on getting V cancelled both sides, we get C is equal to epsilon 0 a by d. This is an expression to find the capacitance of a parallel plate capacitor. By the way, derive an expression for the electric potential due to a point charge. Let us suppose that a point charge, a positive charge, is at the origin. Let B be a point at position vector r bar. Now we have to find the electric potential at the point P. It can be obtained by calculating the work done in bringing a unit positive charge from infinity to that point P. So, the point where we have to calculate potential can be obtained by calculating the work done in bringing unit positive charge from infinity to that point P. The electrostatic force on unit positive charge is plus 1 coulomb at an intermediate point A. Therefore, on applying Coulomb's law, F is equal to 1 by 4 pi epsilon naught into Q into 1 by x square, which is equal to 1 by 4 pi epsilon naught into Q by x square. If dW is the work done in moving unit positive charge against the force through a distance dx, small distance dx, therefore dW is equal to minus force into distance F into dx. That implies dW is equal to 1 by 4 minus 1 by 4 pi epsilon naught into Q by x square dx. Therefore, total work done W is obtained by integrating between the limits infinity to r. Therefore, W is equal to minus integral infinity to r 1 by 4 pi epsilon naught into Q by x square dx. That implies W is equal to minus Q by 4 pi epsilon naught into minus 1 by x within the limits infinity to r. That is equal to minus Q by 4 pi epsilon naught into minus 1 by r, which is equal to Q by 4 pi epsilon 0 r. Therefore, electric potential due to a point charge V is equal to 1 by 4 pi epsilon 0 or 1 by 4 pi epsilon naught into Q by r. By the way, one more important concept that we have to discuss here is what is the equivalent capacitance when capacitors are connected in series. Suppose there are three capacitors of capacitances C1, C2 and C3 which are connected in series to a potential difference V. In series combination of capacitors, we know that charge Q stored on these three capacitors is the same. So what is the factor that changes here? Potential differences. Let V1, V2 and V3 be the potential drops formed on the three capacitors C1, C2, C3 respectively. In series combination of capacitors, the total potential drop is equal to sum of the potential drops on the three capacitors. Therefore, it can be written as V is equal to V1 plus V2 plus V3. But according to the principle of capacitance, Q is equal to C1 V1, Q is equal to C2 V2 and Q is equal to C3 V3 in this case. But V1 is equal to Q by C1, V2 is equal to Q by C2, V3 is equal to Q by C3. I am substituting all these three results in the above equation. V is equal to V1 plus V2 plus V3. We get V is equal to Q by C1 plus Q by C2 plus Q by C3. Therefore, V is equal to, when Q is taken as the common factor, Q into 1 by C1 plus 1 by C2 plus 1 by C3. But when Q is brought to left side, it becomes V by Q is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Effective capacitance V by Q is equal to 1 by C. Therefore, 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So, equivalent capacitance when capacitors are connected in series is 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Therefore, it can be understood that in series combination of capacitors, reciprocal of effective capacitance is equal to sum of the reciprocals of individual capacitances. Now we are going to see the equivalent capacitance when capacitors are connected in parallel. Suppose, as shown in the diagram, that there are three capacitors C1, C2, C3 are connected in parallel in such a way that all positive terminals are connected to one point and all the negative terminals are connected to another point. Here it can be observed that potential difference V remains constant on all these three capacitors. Let Q1, Q2 and Q3 be the charges on these three capacitors C1, C2, C3 respectively. In parallel combination, generally the total charge is equal to sum of the charges stored in all these three capacitors. Therefore, Q is equal to Q1 plus Q2 plus Q3. But Q1 is equal to C1V, Q2 is equal to C2V and Q3 is equal to C3V. The capacitors act as an equivalent capacitor with charge Q Therefore, potential drop V and equivalent capacitance C, Q is equal to CV. Therefore, effective capacitance, effective charge CV is equal to C1V plus C2V plus C3V. On taking V common and get them cancelled both sides, we'll get C is equal to C1 plus C2 plus C3. Therefore, in parallel combination, effective capacitance is equal to sum of the capacitances of these three capacitors. Sum of these capacitances of these three capacitors. In order to apply the balancing condition of Wheatstone bridge, we have to apply Kirchhoff's current law and Kirchhoff's loop law. At any junction in electric circuit, the sum of currents entering the junction is equal to the sum of currents leaving the junction. For the junction B, we will get I1 is equal to I3 and I2 is equal to I4. Similarly, on applying Kirchhoff's loop law, for the loop ABDA, we will get I1 R1 plus 0 minus I2 R2 is equal to 0. Therefore, on simplifying it, I1 by I2 is equal to R2 by R1. Similarly, on applying Kirchhoff's loop law for this loop CBDC, we get I4 R4 plus 0 minus I3 R3 is equal to 0. On simplifying it, we will get I1 by I2 is equal to R4 by R3. So, from the above relations, we write R1 by R2 is equal to R3 by R4. This is the balancing condition of Wheatstone bridge. We are adjusting the resistors such that the galvanometer current IC is equal to 0. Then the bridge is said to be balanced. Use it to determine unknown resistance.